from games and sub-game property equilibrium. Okay, so I asked Chang to review just a little bit of course material and then also solve some examples together. I believe she will work together with you on bargaining game and repetitive game. Okay, so basically I believe she will solve exactly almost the same example again. Okay, the same example, almost the same example I do in my lecture. So if you think everything is super clear to you, probably you will not really want to attend the review session. But otherwise, if you have anything unclear or anything discussed with the TA, then probably it's better to go there to make sure everything is clear to you. Okay? So that's the first thing. And the other thing is that I also posted the second problem set. It's all about, again, extensive form games and sub-game perfect equilibrium. And its due date is next week, okay? So I posted it last Tuesday or Wednesday, I'm not really sure. So probably Wednesday. So, and usually I give you 2 weeks to try all problem questions together with your group members. So the due date is next Tuesday, okay? So again, each group only have to submit 1 copy. So you can basically work with your group members and just make 1 copy and submit that, okay? That's enough. And as I said before, one of the reasons I do this way, the homework thing, is just to encourage you to give you some opportunity to work with your friends, okay? Collaborate. So, okay, and then what is? Bio. Okay, and I believe you are also beginning to prepare your presentation and final on paper. Okay, so I think maybe it's better to remind you again. So every one of you have to submit the term paper at the end of the semester. Okay, it's about real world application of game theory. So basically you choose one possible application of game theory in the real world. For example, you can use some game theory to analyze, for example, the U.S. election last, in 20. When was the last election? I don't know. For example, that's one thing you can do. So you can choose one real-world event, like real-world election, or the real-world some case, some legal case, etc., and then you can analyze it with game theory. That kind of stuff. Okay? And then everyone has to submit their own individual report. But I also encourage you to do research with your group members together. Okay? So, at the end of the day, you have to submit individual report, but it's totally okay and even more encouraged to collaborate with your group members when you do some research. Okay? So, and at the end of the semester, you are also gonna present your group research. Okay? So that's the idea. You have to, okay, so in terms of order of time, you have to present your group research first. Okay? You pick one topic, do research with your group members, and share it with other friends, not only in your group, but other friends as well, all the friends, in this class. And then based on that research, you have to submit individual report at the end of the semester. So roughly speaking, group presentation will be mid-April. That's the end of the semester this year. This semester ends end of April. And the the official end of semester, including everything, final exam, everything will be, I'm not really sure, I have to check again, but probably it's gonna be mid-May. Okay, May 20 maybe, I'm not sure, I have to check it again. So I'm gonna post the exact deadline later on. So that's the idea. Okay? So in terms of presentation schedule, I'm still thinking of what is the best arrangement I can do. I mean, we have, let me check one more time. We have 14 groups. So if I give you 15 minutes for one group, so that means I have to have at least 4 hours. Okay, so I'm still deciding on whether it is better to finish everything in 1 week. Then if that's the case, maybe we have to finish our lecture a little bit later, like 10 p.m. something like that. Or otherwise, I can also separate into 2 days. I mean, half of you do presentation in 1 week and other half of you presentation in the next week. But I'm still deciding. I'm not sure which one is the better arrangement. So I also have to, So it's gonna be determined soon, probably next week or at least mid-March. And as soon as I know the detail, I'm gonna post you details as soon as possible. Okay? Any question? Anything unclear about group presentation and final reports? Okay, so I talked about review session this week, homework due to next week, and also I remind you group presentation and term paper. Okay. Then let's come back to our course material. Last week we discussed some example of repeated game, example of repeated game. So this is our example we discussed last week. So there are 2 players. Player 1, choose either alpha or beta. So the rule is actions. They are actions that player 1 can choose, and columns are actions that player 2 can choose. So player 1 can choose either alpha or beta. Player 2 can choose either alpha or beta. Okay. So and their payoffs are as written in this table. So for example, if both of them choose alpha and alpha, then their payoffs are 3 for player 1 and 3 for player 2. Okay. So this game has. So first of all, this game has 2 Nash equilibrium, 2 pure strategy Nash equilibrium, alpha beta and beta beta. Okay, so I'm not really sure whether there is also mixed strategy equilibrium. Possibly, I haven't really checked, to be honest. But anyway, if you focus on pure strategy Nash equilibria, there are only 2 of them in this game. Alpha beta and beta beta. Okay? But idle equilibrium, alpha beta and beta, both of them are a little bit not really satisfactory in the sense that actually the sum of payoff can be maximized if they choose alpha and alpha. Okay? So in some sense, alpha and alpha is kind of more desirable outcome if you are interested in maximizing the sum of 2 payoffs. But that is not a Nash equilibrium in this case. So for example, if they really insist on, let's say player 1 says, okay, we have to play alpha and alpha, then player 2 will find out that actually in that case it is better for player 2 to deviate and choose beta, in which case he can or she can get 4. Okay, so alpha and alpha is still desirable outcome, but it is not an equilibrium. However, at the end of our lecture last week, however, at the end of the last week's lecture, I actually told you that alpha and alpha can be played, and is in the first period of the game if they play this normal form game twice. Okay, so they repeatedly play this game twice. So there are two periods, period 1 and period 2. In the first period, they simultaneously choose alpha or beta. Okay, and that's the end of the period 1. So they simultaneously choose. So when they make a decision in the first period, they do not observe the other player's action, the other player's decision. So they simultaneously choose. However, the outcome is revealed publicly to both of them at the end of period 1. Okay? So even though they, yeah. Okay, that's it, yeah. And in the next period, basically they play the same game one more time. They simultaneously choose their actions simultaneously together. And then they, at the end of period 2, again, their choices are revealed to both of them. Okay? So basically, both players try to maximize the sum of payoff realized in the first period and the payoff realized in the second period. Okay? So that's the repeated game. So this is actually a extensive form game because there is some dynamics, right? It's not really static. So there is some dynamics, consisting of two periods, period 1 and period 2. And in particular, the second period action can be conditioned on whatever observed in the first period. Okay, so if you draw game tree, it's not really exactly game tree, but anyway, I think it's enough to visualize what's happening here. So in the first period, they play normal form game. So this is kind of, this box is actually, I am supposed to give you more details. So, okay, so they play this game in the first period. And then in the second period, they play the same game again. So this is what happens in the first period, and if the outcome in the first period is alpha and alpha, then this is the game they have to play in the next period, and this is the case when the first period outcome is alpha and beta alpha, and beta and beta. Okay, so this is the the game tree we have to get in this game. Okay, so if you look at this game tree, then you can immediately find out that there are 5 subgames, right? So here we have one subgame here, and this is another subgame. This is another subgame, another subgame. And then the entire game itself is also a subgame. So there are 5 subgames. So the idea of subgame perfect equilibrium requires that their strategy profile has to be Nash equilibrium in all subgames. Okay? Okay, so this is the game tree. Okay, so then the last week I actually showed very briefly, very quickly, I showed that actually if this game is repeatedly as drawn on the board, actually there is subgame perfect equilibrium such that both players choose alpha and alpha in the first period. Okay? So how can we construct such an equilibrium? So this is my proposal. Okay, so let's consider the following, the strategy profile described on the slide. So this is just description of strategy of both players. So remember that a strategy has to specify all plans for action for any contingencies, right? So which means that player one's strategy has to specify, for example, which action to play in the first period, and moreover, player one's strategy also has to specify which action to choose in this case, in this case, in this case, and in this case. Okay? So of course, player one also can randomize. So if it is strategy, sometimes allows. I mean, if player one wants, then of course he also can randomize any cases in any places in this case. And player two's strategy also has to specify which action to take here, 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 and here. Okay? Okay, so then this is my proposal of equilibrium strategy profile. So let's say both players choose alpha in the first period. So both players' strategies specify to choose alpha in the first period. Okay? So they choose alpha and alpha in the first period. And if both players choose alpha in the first period, so that means they play this part of the game tree in the second period. In this case, here, according to the strategy profile on the screen, they choose alpha and beta in the second period. Okay, so this one. Otherwise, so there are other remaining possibilities. So in all three possibilities, in all three cases, they choose beta and beta in the second period. Okay, so that's the strategy. Okay, so if they play this strategy, then they choose alpha and alpha in the first period. Okay, and alpha and alpha, that outcome in the first period is revealed at the end of the first period. So they will play alpha and beta in the second period. So the outcome will be, on the equilibrium pass, the outcome will be alpha and alpha in the first period and alpha and beta in the second period. And player one's payoff will be 3 plus 0, which is 3. Player two's payoff is 3 plus 4, which is 7. Okay? So what is important here is that even if these 4 games are not reached in equilibrium, so they are off the equilibrium path. Even if they are off the equilibrium path, we have to specify their strategies in all 3 cases as well. Okay? Okay, then let's check whether it is indeed subgame perfect equilibrium or not. So we have to check all subgames. So let's begin from this case, this subgame. So this is just, if you focus on this subgame, so this is just a normal form game, right? So according to our definition of subgame perfect equilibrium, they have to play a Nash equilibrium, which is true, right? They are supposed to play alpha and beta, but alpha and beta happens to be Nash equilibrium here in this normal form game. So we are okay here. We are fine here. It's okay here. And then what about these cases? So they are supposed to play beta and beta in all 3 other cases. And indeed, beta and beta is also Nash equilibrium for this normal form game. So remember that beta and beta is actually a subgame, a Nash equilibrium for this normal form game. So okay, so in second period, in all subgames in the second period, they actually play Nash equilibrium. Okay. Then what about the entire game? So in order to make sure, in order to check that this strategy profile is Nash equilibrium for the entire game, we have to show that no player has product of deviation in the first period as well, right? So then let's see indeed if no player has product of deviation. So let's begin with player 1. So if this guy played as planned, if this guy play equilibrium strategy, then his payoff in the first period is 3, and then second period is 0. So the total payoff is 3, right? But if this guy player 1 deviates, so that means this guy chooses beta in the first period. So payoff in the first period is 0. And then, but still player 2 sticks to the equilibrium strategy. So which means that the outcome in the first period will be beta and alpha. Okay, so then this is the game they have to play in the second period. So they play beta and beta. So payoff in the first period, second period is 0. So which means that if player 1 deviates, then his payoff will be 0. 0 in the first period, 0 in the second period. Okay? But equilibrium strategy guaranteed 3, right? So which means that player 1 also has no reason to deviate in the first period. So that shows that player 1 has no incentive to deviate here, and we already have shown that player 1 has no incentive to deviate here, 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 and here. Okay? So player 1 has no incentive to deviate at any places in this game. What about player 2? If player 2 follows the strategy profiles in equilibrium, then his payoff in the first period is 3, and in the second period it is 4. So the sum of payoff is 7. But if player 2 deviates, then what happens? Then this is the outcome in the first period, in that case, which means that player 2 enjoys 4 in the first period, which sounds good. However, so player 1 chooses alpha, player 2 chooses beta. So then in the second period, this is the game they have to play if player 2 deviates in the first period. And they play beta and beta, which means the payoff for the player 2 in the second period is 0. So summing up two numbers, the total payoff for player 2 will be 4, right, if player 2 deviates. But that is smaller than 7, which he or she could get in, if player 2 follows the equilibrium strategy. So player 2 also has no reason to deviate. Okay? So I just have shown to you that all players have no reason to deviate in any places in this game. Okay? Or to put another way, this strategy profile is Nash equilibrium for all sub-games. This sub-game, this one, and the entire. Okay? So remember that when we say a strategy profile is Nash equilibrium, it simply means that no player has deviation, profit of deviation, right? Okay, so this is one possible equilibrium, and indeed in this equilibrium they play alpha and alpha in the first period. Okay? So this example highlights that if you play a normal form game repeatedly, the outcome can be very different compared to the case that the same game is played just one time. Okay? So this is just one equilibrium, and there are two more comments. Okay, so comment one. So, okay, we just mechanically checked this is this one on the screen is sub-game perfect equilibrium. And intuitively, what's really going on here is that, okay, so this equilibrium strategy profile is something like some kind of proposal that, okay, so let's play alpha and alpha together in the first period, okay, which is good outcome. So, and however, we also understand that player 2, especially player 2, has some reason to think about deviation, right? Because, 4 is rather than 3, so alpha and alpha is actually worse than alpha and beta in terms of player 2's perspective. So player 1 understands that player 2 will be tempted to deviate. So what's player 1 can propose is that, okay, let's play alpha and alpha in the first period. Then if player 2 follow this plan, then I'm going to reward you by playing a good equilibrium in the second period. So alpha and beta is supposed to be good equilibrium because compared to beta and beta, because player 2's payoff is 4 in alpha and beta, but in beta and beta, player 2's payoff is 0. And if player 2 deviates, then I'm going to punish you by playing a worse equilibrium in the second period. Okay? So this kind of intertemporal incentive scheme can incentivize player 2 to play alpha in the first period. And that kind of intertemporal scheme was impossible in the case that this game is just played once. Okay? So that's intuitively what's going on here in this equilibrium. So that's comment 1. And comment 2 is that, okay, I just gave you one possible subgame perfect equilibrium. And the thing is that actually, if you asked me if there is any other subgame perfect equilibrium, and the answer is yes. Okay? So I just give you this example because this example is supposed to be presumably kind of interesting equilibrium because alpha and alpha is played in the first period. But there are also many other Nash equilibrium. There are also many other subgame perfect equilibrium. Okay? So for example, there is for example, one possible equilibrium is such that they play alpha and beta in all subgames, in all cases. Let's say they play alpha and beta in any cases, then this is actually Nash equilibrium. I'm sorry, subgame perfect equilibrium. First of all, this is Nash equilibrium for all these subgames, right? Because alpha and beta is Nash equilibrium for the normal form game, state game. And at the same time, you can easily check that, given this arrangement in the second period, both players also have no incentive to deviate in the first period. So you can quickly check this is also one possible subgame perfect equilibrium. And actually there are more. Okay? But here I just highlight this particular example to give you some interesting result. Just one interesting example. Okay? Any questions? Okay, so actually theory of repeated games is actually really complicated, and there are a lot of things we can discuss about repeated games. So it's very complicated, and it's a really voluminous in terms of quantity as well. So you can actually write a book solely on repeated games. But I'm not really interested in giving you some general theory of repeated game this course. I mean, I just wanted you to give you some examples that highlight why repeated games are interesting. Okay, so that was our first example, and let me give you the second example. So this example is actually a prisoner's dilemma. Okay, so so this table is prisoner's dilemma game. So maybe I use different letters to stand for actions of each players. But EE, they are supposed to be corporation, and S is supposed to be some betrayal. Okay, so I think E is for effort in this particular representation. So both players can either put some effort or shirk. Okay, so if both of them put effort, then outcome will be good. So both of them can enjoy quite good payoffs, which is 2 in this example. And if both of them shirk, then outcome will be bad, which gives both players 0. But the thing is that if player 1 puts effort, then player 2 has some incentive to free ride. Okay, so if player 2 shirks, then his payoff will jump from 2 to 3 in sacrifice of player 1's payoff. So player 1's payoff drops to -1, but player 2's payoff will jump to 3 if player 2 deviates. Okay? Okay, so that's the prisoner's dilemma game. So I don't really think I have to solve this game again. It's actually really easy to see that there is unique Nash equilibrium, and in that unique Nash equilibrium, both players choose S, shirking. Both players will shirk in this unique state equilibrium. Actually, you can easily check that shirk is actually dominant stretch. Okay. Okay, so one potential message of prisoner's dilemma game is, this message is actually the message is very pessimistic, right? I mean, they potentially can get some nice outcome if both of them cooperate together, but in equilibrium, both will shirk, so both of them free ride, so the outcome will be bad. Okay? So naturally, many people actually have proposed how to escape this negative outcome. Okay, and one potential solution is, okay, so then we already shown that repeating the same game multiple times sometimes give you some nice equilibrium, right? Which was impossible in the static case. So one natural attempt is, okay, so let's make this game, let's make them two players play this game repeatedly. Then let's see, whether we can have a better equilibrium outcome compared to the case that the game is played just once. Okay? Okay, so in this particular example of prisoner's dilemma game, I'm gonna introduce discounting factor. Okay, so we are gonna first consider the case that the game is repeatedly finitely many times. Let's say capital T times. And basically the rule of the repeated game is very similar to our first example. Let's say capital T is 2, so they play this game twice. Then they choose action in the first period simultaneously, and then the outcome is revealed at the end of the first period, and then they play the same game again in the second period. Okay, they choose action in the second period simultaneously. Okay, so but however, differently from our first example, I'm gonna introduce this counting factor, which means that payoff realized in the first period is more valuable than payoff realized in the second period. Okay? So just as we did for the bargaining game. So delta 1 and delta 2, delta 1 means discounting factor for player 1 and delta 2 means discounting factor for player 2. But we are going to actually assume that they are the same, and we use this notation delta without any subscript. 2 stands for both players' discounting factor, and discounting factor is any number between 0 and 1. So okay, so discounting factor means that, for example, if EE is outcome in the first period and SE is outcome in the second period, so discounting factor means that the total payoff for player 1 will be 2 plus delta times 3. Okay, so the payoff realized in the second period is discounted, and payoff for the player 2 is, in the same case, 2 plus minus delta. Okay? Okay, so this is the setup of the repeated prisoner's dilemma. Okay, so let's begin with the simplest case such that capital T is 2. Okay, so what is sub-game perfect equilibrium for this case? If they play prisoner's dilemma twice. Any idea? Can you speak up? Yeah. SS what? For the first period, and then in the second period? SS. Okay, so you mean that the sub-game equilibrium will be something like they shirk all the time, right? Okay. Actually, that's correct. Actually. Okay, so let's check. Let's solve this game together. So answer will be S all the times. Let's check in this is true and in more systematical way. Okay, so here we are considering the case that capital T is 2. So if you draw the game tree, then that will be similar to this one, right? So we have to use different letters and different numbers, but the shape of game tree will be similar to this one. Okay, then we can solve this game by backward induction, as always. And let's think about what happens in the second period. So in the second period, they play prisoner's dilemma game, just normal form game in the second period, right? But we know that there is unique Nash equilibrium for that sub game, S and S, right? So which means that in all 4 sub games in the second period, in this case, in all sub games in the second period, they have to play S and S in the second period. Okay? So then let's think about what players will choose in the first period. Okay, so in the second period, they understand that in the second period, the outcome will be S and S. Okay? So that's kind of fixed. There is no way to change it. Even if I choose E in the first period, we will play S and S in the second period. Right? So that kills actually any reason to cooperate in the first period as well. Right? So one potential reason to cooperate in the first period is, if something like, if I cooperate today, then you will cooperate in the next period as well, right? But we already know that there is no cooperation in the second period. Absolutely no cooperation. Then you also have no reason to cooperate in the second period, right? So which means that, you have to choose S sharp in the first period as well. And that's only sub-game perfect equilibrium for this game. Okay? Yeah, let me put slightly different way. Okay, I think it's clear to all of you that why SS will be played in the second period, right? In all cases. And let's focus on the first period. Okay, so if we play E and E in the first period, okay, so this is the payoff I will get. If we play E and E in the first period, then player 1's payoff will be what? 2 and 2. 2 in the first period. And in the second period, we know that both of them will play S, right? So delta times 0 is player 1's payoff eventually if we play E and E in the first period. So first E is player 1's action and second E is player 2's action in the first period. Okay? So similarly, player 2's action will be, payoff will be the same. Okay? And if player 1 chooses E and player 2 chooses S in the first period, then player 1's payoff will be what? -1 in the first period, right? Plus, again, 0 in the second period, right? Because we know that there will be no cooperation in the second period. So which is -1. And what about player 2? So player 2's payoff will be 3. And 0 in the first period and 0 in the second period. So it's gonna be 3. And if they choose S and E in the first period, then you can easily calculate player 1's payoff is now 3, and player 2's payoff is now -1. Okay? So the same calculation, but here it is player 2 who puts effort in the first period, so his payoff is -1, while the other player's payoff is 3. And if both of them choose S and S in the first period, then what happens? Player 1's payoff will be 0 in the first period and 0 in the second period. So payoff is 0 for player 1, and similarly, player 2's payoff is 0. Okay? So when I calculate these payoffs, I use the fact that outcome in the second period will be S and S in all cases. Okay, then if you look at this payoff function, so U1 is 2, U2 is 2 if the outcome is E in the first period, and ES, if the outcome in the first period is ES, then U1 is -1, U3 is 3, etc. Then you can realize that this is exactly the same payoff you can see on the table. Okay? So which means that once you fix S and S in the second period, the game they play in the first period is just exactly equivalent to the static prisoner's dilemma game. Right? And we know that in prisoner's dilemma game, S is strictly dominant strategy. So which means that in period 1, both of them also have to choose S in the first period as well. Okay? So we use backward induction, and our result